Okay, thanks for watching my video today. Let's represent another integral representation for the Euler-Mascheroni constant. Okay, so then is prove that the integral from 0 to 1 of 1 upon t plus 1 upon log 1 minus t dt is equal to our Euler-Mascheroni constant. Here I'm writing this analogy as ln. Okay, I used to forget to write ln. Okay, so here analogy is nothing but natural logarithm. Okay, here I use natural logarithm. Now let our integral to be I, then is integral from 0 to 1 of 1 upon t plus 1 upon log of 1 minus t dt. Now separate them, then is integral from 0 to 1 dt upon t plus integral from 0 to 1 dt upon log 1 minus t. Now put log 1 minus t is equal to negative x, implies that 1 minus t is nothing but e to the negative x. Okay, this is the root of x, the root of exponential and this natural logarithm. Okay, if you differentiate it, negative dt is negative e to the negative x dx. So negative is not there. They will cancel out already, right? When t tends to 0, then x tends to 0. When t tends to 1, then x tends to infinity, right? And here also I'm just substituting, okay, so that the variable will be the same thing. T equal to x, dt equal to dx for this integral. Okay, therefore I is equal to integral from 0 to 1 dx upon x plus integral from 0 to infinity e to the negative x upon negative x dx. Okay, which is equal to integral from 0 to 1 dx upon x minus integral from 0 to infinity e to the negative x upon x dx. Okay, now we are going to use the limit representation for this exponents here. Okay, therefore our integral I is integral from 0 to 1 dx upon x minus integral from 0 to infinity 1 upon x. So the limit representation for e to the negative x is limit n tends to infinity 1 minus x upon n to the power n dx. Okay, so now taking out this limit here outside the integral, so I is equal to limit n tends to infinity of integral from 0 to 1 dx upon x minus integral from 0 to, since this is also infinity and this n tends to infinity, then this is nothing but n, right? Integral from 0 to n only 1 minus x by n to the power n upon x dx. Okay, again this one, due to our property of definite integral, integral from a to b is same as integral from a to c plus c to b, right? I hope this is clear. So I is equal to limit n tends to infinity integral from 0 to 1 dx upon x minus integral from 0 to 1 1 minus x by n to the power n upon x dx minus integral from 1 to n 1 minus x by n upon to the power n upon x dx. Okay, then this, because of this property, so 0 to n can be split as 0 to 1 to 1 to n. Okay, now since these two limit are upper and lower limit are same thing, so we can do something here, right? Therefore limit n tends to infinity of integral from 0 to 1 1 minus x upon n to the power n upon x, so the denominator are the same thing, dx minus integral from 1 to n 1 minus x by n to the power n upon x dx, right? Now adding and subtracting integral from 1 to n dx upon x. Okay, adding and subtracting, then limit n tends to infinity integral from 0 to 1 1 minus x by n to the power n upon x dx. Here plus, I'm going to take plus first, plus 1 here, here will be 1, right? 1 minus x by n to the power n upon x dx minus, so the integration of this one will be integration of 1 over x is log x, right? Natural logarithm of natural log x. Okay, so the limit is from 1 to n, so it will be log n minus log 1, right? Log 1 is, we know it is 0, so it will be log n, right? Now okay, now because of this our property, okay, because of this property we can have again that, or this integral this two from 0 to 1 and 1 to n, we can combine in 1 again, so limit n tends to infinity integral from 0 to n 1 minus x by n to the power n upon x dx minus log n. Okay, right, this is clear, I think. Now we're going to use substitution method here. Substitute that, put x by n is equal to u, so which is x equal to n u, so dx is n du. Here n is constant. Okay, when x tends to 0, u tends to 0, and x tends to n, then u tends to 1. Then we have in the next page. Okay, we are going to continue here. We have to continue in the next page. Okay, here we substitute now. Here I is limit n tends to infinity, integral from 0 to 1, right? 1 minus u, here x by n is u, right, to the power n upon n u, x is nothing but n u, into dx is n du minus log n. Okay, so therefore I is limit n tends to infinity, integral from 0 to 1, 1 minus u to the power n upon u du minus log n. Okay, here this n, they will get cancelled out already. Okay, now let's do substitution again. Put 1 minus u is equal to theta, which is equal to, if you differentiate, negative du is d theta, so du is negative d theta. Okay, when u tends to 0, theta tends to 1, u tends to 1, theta tends to 0. We have the limit n tends to infinity, integral from, when u tends to 0, then theta will tends to 1, right? 1 to 0, 1 minus u is nothing but theta. Okay, theta to the n upon, you find out here u, so 1 minus theta. Okay, 1 minus theta, and du is nothing but negative d theta minus log n. So because of this property, integral from a to b is nothing but negative of integral from b to a. If you apply negative, the upper and lower limit will be changed. Okay, they will interchange. So because of this negative, so these two I can interchange them. Then this limit n tends to infinity, integral from 0 to 1, 1 minus theta to the n upon 1 minus theta d theta minus log n. Okay, we know that this part, the integrand is same as this, is same as this one. Okay, so this is what we call, or gp. So sum from k equal to 0 to n minus 1, x to the k is 1 minus x to the n upon 1 minus x. Okay, exactly the same thing here. Replace x by theta only. Okay, therefore our integral I is limit n tends to infinity, sum from k equal to 0 to n minus 1, integral from 0 to 1, theta to the k d theta minus log n. This summation is constant. Okay, we treat it as constant, that's why it's coming out outside the integrand. Okay, integral. So I is equal to limit n tends to infinity, sum from k equal to 0 to n minus 1. So integration of theta to the k with respect to theta is theta to the k plus 1 upon k plus 1 from 0 to 1 minus natural log n minus limit n tends to infinity, sum from k equal to 0 to n minus 1 upon n minus 1 upon k plus 1 minus natural log n. So which is I is equal to limit n tends to infinity, sum from k equal to 1 to n 1 over k minus log n, which is equal to this limit, what we call, this limit is what we call our Euler-Mascheroni constant. Okay, therefore our original integral then is, or integral this one, this integral from 0 to 1, 1 upon t plus 1 upon log of 1 minus t dt is nothing but or Euler-Mascheroni constant. Okay, this is how I managed to prove this, the Euler-Mascheroni constant representation. Okay.